Dr. Neumann, shall we begin?
Yes, let's begin.
Thank you for joining us today, Doctor.
Pleasure.
It's a pleasure to have you here.
Pleasure.
Could you please tell us about your work and your educational background?
Well, to start off with, my passion lies in the intricate dance of numbers and the enchanting possibilities of electronic computers. The delightful world of mathematics and computer science is where I like to spend most of my thoughts. On a more technical note, I completed a 2-year non-degree program in chemistry from the University of Berlin. Along with that, I completed my degree in chemistry from ETH Zurich. Then I went on to complete my PhD in mathematics from the Habib University. After all of this, I went to work under the great David Hilbert. And if you must know, as part of my thesis, I wrote on the axiomation of Cantor's set theory.
Impressive indeed. I'm fascinated by your work.
Thank you.
I heard you have contributed to physics too, quantum mechanics and statistical physics. Would you like to elaborate on that, please?
The quantum mechanics, the realm of minuscule and the mysterious. It's like a sophisticated tango of particles. As for statistical physics, imagine a grand ball where entropy swirls in an elegant dance. These endeavors complement my work in other areas, providing a rich tapestry of understanding.
Interesting. Given the social and political conditions due to the ongoing war, how do you envision your expertise contributing to this highly classified effort?
Well, my friend, even in times of war, even during times of war, as I may say, even the numbers, they act like soldiers. The electronic computers I'm currently working on could prove to be the generals leading the charge against the Nazis, because they will help aid the calculations with strategy. My work, I believe, will enable us to develop a revolutionary machine that could possibly calculate the feasibility of the atomic bomb. A possible technical revolution, if I may say.
Could you please elaborate on your research on the computer architecture side of your work?
Well, as I told you, my research mainly focuses on set theory. So, now employing this art of set theory will play a crucial role in the foundation of modern and future computer design. Currently, I am working on a computer architecture which will allow for the separation of the memory processing unit and, my apologies, for the computer memory and the processing unit, allowing for what I will deem the stored program concept.
I have heard, it came to my knowledge that Mr. Alan Turing is also related to your field. What are your opinions on someone like Mr. Alan Turing working on this field and his theories about this field?
Alan Turing, a fellow dancer in the grand ball of computation. His expertise and knowledge, I believe, can revolutionize code breaking. The Nazis, if you know, have the Enigma machine, and it is proven to be a lot more dangerous than we could have possibly imagined. But the mathematical prowess of Alan Turing, I believe, will prove fruitful in breaking the Enigma and giving our boys a winning chance in this war.
Like every scientist, their work is criticized. Some aspects of your theories have been proven false over time. How do you handle challenges and criticism of your theories?
Well, the humbling waltz of scientific discovery. You see, my friend, admitting a misstep is like gracefully twirling on the dance floor. It allows for a more refined performance. The pursuit of knowledge is never ending, and sometimes you just need to change partners and perspective. Mistakes, yes, they will help you learn, but they will help you learn.
Given the criticism, have there been any scientists or people that have criticized or acknowledged your work? How do you respond to such feedback as well?
Oh, the symphony of opinions. Einstein, a distinguished conductor, appreciates the melody, while others may find a dissonant note. But my friends, criticism is the spice of the scientific life. It keeps us on our toes, if you know what I mean. Or perhaps our dancing shoes. Same to same. Also, may I add, I am truly honored that someone like Hans Beta has called me a prodigy. It is truly humbling and truly an honor to be given such a high admiration from such an esteemed man of science.
Well, thanks for being here, Doctor. We have Mr. Alan Turing coming in right now.
No
It
problem.
was fun having you here.
It was great. It was a pleasure. I hope to be on the next.
Thank you for joining us, Mr. Turing. It's a pleasure to have you here. We have concluded our interview with Mr. Neumann. Given that you guys share the same interests and have collaborated on several occasions, what are your opinion on his work?
Certainly, John and I have had the privilege of working together on several occasions, particularly in the realm of theoretical computer science. His insights into electronic computers have been foundational for my own work.
Could you elaborate on the collaborative aspect of your work with Dr. von Neumann? How did you complement each other's research?
Well, you see, John focused on the hardware and nitty-gritty of electronic engineering, while I took a more theoretical approach. It was a symbiotic relationship, really. His practical knowledge and my abstract thinking melded into something greater than the sum of its parts.
What do you think? How does Mr. Newman's work affect the field of computing and beyond?
Well, John's contribution extended far beyond our collaboration. His architecture revolutionized how we design and build computers. The stored program concept he introduced became the standard, enabling the development of more powerful and flexible machines. His legacy is embedded in every computer we use today.
Considering that you are an expert in theoretical computer science, what do you think Mr. Newman's practical approach to electrical computers?
Well, the job requires a balance, doesn't it? John's practical approach is crucial. It ensures that theoretical concepts find real-world applications. His work provides a bridge between the abstract and the tangible, making him quite suitable for a position that demands both depth and practicality.
Well, thank you for your time, Mr. Turing, and sharing your insights with us. Your input has been very valuable, and your collaboration with Mr. Von Neumann is invaluable. Hi, Doctor. It is nice to have you back here with us again. Because of the sensitive nature of this project, I think it is best I keep my camera closed because I don't want to disclose or reveal any clues to my location.
It is good. It is good to be back for the interview. I'm glad we're having a follow-up.
So, Mr. Newman, would you please elaborate how would you contribute to the Manhattan Project?
Yes. Well, as you see from my appearance, you can tell that since our last interview, I've been continuously thinking on how we can better work on the project. Now, you see, I have come up with a basic architecture. Now, following the stored program concept I talked about in our last interview, I believe we can develop a machine such that it has three parts, to so to say. So we will have the input and the output unit, which will receive data from the outside and give you calculation from the computer. So now in the middle, there will be two units. One will be a sort of like the memory, where everything will be stored. And then you will have the brain, a sort of processing unit. So altogether, you can give this sort of device multiple inputs. So in one go, multiple values to be calculated and the different operations that have to be performed, the addition, the subtraction, the logical operation like and, or. So all of these values together, large, multiple of these could be sent to the device together. Now, when this happens, the processor will, the device will take the input and it will store it in the memory. Now, along with now within the memory itself, there will be two sections. one which will be storing the instructions on the how should I say what will be performed for the given instruction being inputted, like the calculations on the electronics to be performed for the addition operation, for the subtraction operation, those kind of details. And the other are where the values and what operations to be performed will be stored. So now, once all of the data is in the machine, the processing unit will have a sort of like a controlling unit. This unit will bring will bring the data from the memory and send the data back to memory to be stored if need be. Now, once the data is brought from the memory, it will be transferred to a sort of arithmetic and logic calculating unit. So I will be I would like to call it the ELU, arithmetic and logical unit. This this is essentially where all our calculations and logic will be performed. And from here, data will be sent back to the memory to be stored through the control unit or it will be outputted to the user. And along in this with this, the traveling of data will be overdone using buses. Buses will take the data from the input to the memory, from the memory to the processing unit to the output across all of them. We will have, I am currently working with my perspective of three buses, a data bus, a control bus, and an address bus. Each will have a different purpose and they will pass electronic signals of the data from these different units. Now, another thing that I will have that I'm thinking of is that within these units, there will be different temporary memory units in them, which will temporarily store the data, such as given that there's a bulk of instructions that have to be carried out being inputted, this register will one by one, for example, a register in the control unit will store one of the instructions that has to be performed, the immediate instruction. So it'll take the instruction and store it in itself while it is processing, while the processor is processing. Another register will have is one which will store the next instruction, which will have to be fetched. Another can have the data currently being processed that will be being stored. We will have a register that will store the output of the calculation that is performed before it is outputted. So like this, you will have multiple registers. A uh, what? How do I say this? An accumulator of sorts, uh, memory data register, a current instruction register, a program counter, the one which will point to the next instruction, and many, roughly two, three more we will have in this to store the data temporarily for the processing. Now, this machine we can build it using multiple capacitors, transistors, the relays, and the multiple switches, all of these, and vacuum tubes. And combining them all of this, we can create a brilliant electric circuit which can help perform huge, enormous mathematical calculations. Now, I believe most of the scientists working on the Manhattan Project will find it very useful, given that we are working and talking about atomic bomb. It is a very, very, very large scale invention we are talking about. We will have to perform calculations with the very big magnitudes. Now, these are calculations which, if done by hand, can have error. But if they are done by a machine so precise, we can be sure that we are not wrong in our calculation. And because of this, less resources will be wasted, which will help make our project run more efficiently without wastage. And I believe this will help a lot of the scientists working on the project, and Dr. Oppenheimer will find it very useful.
Thank you, Doctor, for your insights. Seeing that you are really interested in working with us and that your criteria and your resume in mathematics speaks for itself. Your expertise will help us in the Manhattan Project. So, after careful consideration, we are pleased to extend an offer for you to join the Manhattan Project.
Thank you, thank you. I would love to work with the greatest minds of our generation. It would be an honor for me. Thank you very much. I would love to work. And hopefully we will be successful in creating a weapon such that it will finally put an end to the destruction caused by the fascist Nazis. Thank you very much. I am deeply humbled and deeply honored.
Your
And
unique skill set is precisely
this
what we needed. After seeing all this and meeting Dr. Alan Turing and hearing his thoughts about your work, we have decided that you are the man for the job.
thank you.
Now, I will like to conclude our interview and will thank you for being here.
I hope to see you on the secret sites
All,
of the project.
all right. Have a good one, doctor.
Thank you. Goodbye.